Yes, hello guys. Today I have to talk about what is Leibniz theorem. Now, in case of Leibniz theorem, as I promised that I'll discuss this in 33rd lecture. So today I'm taking this. Okay, what is Leibniz theorem? I will describe who was Leibniz. Okay, so let me first introduce what Leibniz theorem. All these questions are based upon Leibniz theorem. I have to find out nth derivative of all these questions with the help of Leibniz theorem. So Leibniz theorem is used for what? Why Leibniz theorem is required? Okay, Leibniz theorem is used for, first of all, product of two functions. If there is product of two functions, okay, there are two functions given in product form, then we have to find out nth derivative of this. Then in that case, Leibniz theorem is used. Okay, so let me first introduce what is Leibniz theorem, and before that, brief history of Leibniz. Who was Leibniz? Leibniz, Mr. Leibniz, his full name was okay, Gottfried Wilhelm Leibniz. Okay, Wilhelm Leibniz. Okay, his time period was 1646 to 1716. Okay, he was a German mathematician. He was from Germany, basic German mathematician, but he was independent inventor of the differential calculus. Okay, he contributed a lot into differential calculus. Okay, independently without any support from any side. All right, but it is being said that there was a dispute among a supporter of Newton as well as of Leibniz, that Leibniz was the inventor of differential calculus or some formula of differential calculus, or it was taken from Newton's side, or Newton was the initial inventor of differential calculus. So this dispute was there, but finally Leibniz clarified in 1775. Okay, he described that there was a discussion in the there was a conversation between Newton and Leibniz, because they were contemporary. All right, so there was a mutual communication through letters between Newton and Leibniz, but there was nothing was stolen by Leibniz from Newton's side, but there was a mutual discussion among them. Okay, so they were contemporary. So it is not but his contribution in case of differential calculus is much. Okay, it cannot be forgotten about. All right. First of all, he gave these denotations dx dy, which is differentiation of x with respect to x. Okay, this is differentiation, and differentiation of y with respect to y, or this is differentiation of y with respect to y maybe. Okay, and sign of integration he gave this y dx. This formula also he gave. Finally, he gave this y dy, which is equal to 1.2 y square. This, which we use nowadays, was also given by him. So Leibniz has contributed a lot. He was one of the initiators of differential calculus. All right, so we can't forget his contribution. So what is his theorem? Now let me discuss about what is his theorem. So he gave this Leibniz theorem, which is used mostly for when two functions are in product form. When two functions are in product form, then Leibniz theorem is used. Then Leibniz theorem is used. I'm sorry, this is Leibniz theorem. Then Leibniz theorem is used. Let me write it again. Then Leibniz theorem is used. So what is this? Suppose y equal to u and v, u into v, where u and v are functions of x, where u and v are functions of x. Okay, where u and v are functions of x, then yn, the nth derivative of y or yn is given by, let me take n.C.r, this is un into v, plus nc1 un minus 1 v1 plus nc2 un minus 2 v2 plus and so on. Let me take another functions nc3 un minus 3 v3 plus and so on. Finally, it is u vn. Okay. So this is the theorem of Leibniz theorem. So this we will prove. I have to prove it through induction, mathematical induction. I'll prove it. Okay, but before that, this is the theorem where nc0 is combination formula. nc0, it is 1. This is nc1 is n, and this nc2 is n into n minus 1 factorial 2, etc. Alright, so this is the formula which Leibniz gave. Okay, this Leibniz theorem is mostly used for finding out nth derivative of two functions when they are in product form, like this u and v. Okay, so I've taken this u and v two functions. Now let me prove this through mathematical induction. I mean, how this theorem is this theorem true for for number of values? If I find out first time, let me take n equal to here 1, 2, 3 and so on, or let me first then assume that this is true for n equal to k or n equal to m. Then I have to prove that this is true for and next term m plus 1. Okay, so if n plus 1 is true, same formula is obtained for n plus 1 after differentiating mth term or mth derivative. Further, that will give us ym plus 1. Okay, I'll take n equal to m to be taken as true. Okay, it is true for n equal to m, suppose. Okay, then I have to differentiate that function or that equation with respect to x again. Then we will obtain ym plus 1. If it is the same formula is obtained, okay, after differentiating by mth term, okay, by mth derivative, then we will say that okay, this theorem is true for all types of functions or all integral values, right? 1, 2, 3 and so on. So this is how we have to prove it. So this is Leibniz theorem. I'm going to prove it, and then I have to find out these questions which I have taken from online queries. Okay, most of the questions are asked by the students. I'll prove them that how their nth derivative is found, or whatever is given there, that is to be proved by me. So let me first prove this theorem. Okay, and let me prove the Leibniz theorem. This is very important theorem, one of the important theorems in differential calculus, and with the help of this we find out what is the product form. So if I take n equal to 1, let me take n equal to 1. So y1 first time derivative, here these suffixes, okay, n, this is nth term 1, 2, 3 and so on, 1, 2, okay, all these suffixes denotes differentiation of that function, okay, that time. This is nth time, this is first, this is n minus 1 time, this is n minus 2 time, this is second derivative, this is first derivative, like this. All suffixes denotes differentiation, alright, derivative. Now let me take y1. So this will give us, if y equal to u.d, okay, then first time derivative is, we know that first function as it is, or u1 into v plus u v1. This we know by product formula. Okay, this is product rule which we have already described, that what is product rule and quotient rule and all. These formulae are also given by Leibniz. Quotient formula and this product formula, they were given by Leibniz. Okay, so Leibniz theorem is also very useful in case when we have to find out nth derivative of these two functions which are in product form. Alright, so this is first time we know this is derivative of. Now let me take second time derivative of this. So this will give us u2v plus u1 v1. This is of this second time. First function derivative of first, second as it is, or first function as it is, first function as it is, derivative of second is v1, and then second derivative as it is, derivative of first, which is u1, so it will be u2. Okay, now let me again differentiate this one. First function, differentiation of first, second as it is, or vice versa. Then second function, first function as it is, derivative of second. So this will give us second derivative of u, first as it is, which is twice u1 v1 plus u v2. This is second derivative. So this is we have seen here that okay, this is true for first derivative, second derivative. Now let me take that this formula is true for n equal to n. So let me take it is true for, let us assume that this is true for n equal to m. Okay, so ym is equal to, let me take u m v. nc0 is 1, so that are nc0 is 1, that are not taken. Then plus this is mc1 um minus 1, this is v1 plus mc2, okay, um minus 2 v2 plus mc3 um minus 3 v3 plus and so on. Okay, let me take rth term. This is n.C.r um minus r. This is vr plus mc. Okay, this is r minus r plus 1, because next term from r will be r plus 1 term. This is m minus 1. Okay, then this is m minus r. This is r. We are adding this 1, 2, 3, and 1, 2, 3, and so this is r plus 1. So this will be u m minus r minus 1, because r plus 1, if we subtract this r plus 1 from minus sign, both negative, and this is v r plus 1. Okay, so vr plus 1 plus and so on. Last term will be u v m. Okay, this is vm, u vm, un v, last is u vm. Okay, this is true for, let me take this is true for first, second, third, third. Now we have assumed that this is true for n equal to m. Now I have to differentiate this to obtain ym plus 1. Okay, this is, if it is true for the same formula is obtained for ym plus 1, then we will say that this theorem is true for all the integral values of n. Alright, so now let me differentiate this. Differentiating it with respect to x, with respect to x, we get, now let me first differentiate this function. So here we get ym plus 1, because we have differentiated m further, it is ym plus 1 term. Okay, so now um plus 1 is to be differentiated first time. It will be um plus 1 v as it is, now plus as it is v1. Okay, plus if mc1 I take common, okay, within brackets it will be in two terms, it has to be differentiated. It will be only. If I differentiate this further, m plus 1 minus 1 cancel out, so this is only, and v1 as it is. Now plus minus 1 as it is v2, this is v2, this is differentiated. Now taking mc2 common, okay, and this is minus 1 less, because we are differentiating it, and v2 as it is, plus now minus 2 as it is, this is v3, differentiation of v2, v3, okay, plus mc3, and differentiation of minus 3 means minus 2, and v3 as it is, plus minus 3, and this is v4, etc. And let me take rth term, n.C.r common, and this will be minus r plus 1 we are adding 1, and this is we are as it is. Let me take common. Now plus u m minus r as it is. This is v r plus 1. Okay, plus, and this n.C.r plus 1, let me take n.C.r plus 1 common. Within bracket it will be um minus r plus 1 means m minus r only. Okay, for plus 1, if we add minus 1 plus 1 cancel out, and v r plus 1 as it is, plus sign this um minus r minus 1 as it is. This is v r plus 2. Okay, and plus and so on. And final term, this is u vm plus 1. This is m plus 1 term. Before that it will be u1, okay, the last term, and the other terms will also be there. Now let me summarize them. Okay, let me take common. So what we obtain here, this is now one formula which, let me write here, if it is n.C.r plus n.C.r plus 1, it will be equal to n plus 1 C.r plus 1. This is the formula we know. And if I just apply this, for example, if it is 4C1 plus 4C2, it will be 5C2. This sum will be equal to this one. It's the same formula, n.C.r if it is, and n.C.r plus 1. This is next term. This next term will come here, and this 1 will be added to the same this denomination. Okay, so this is m 5nc1, like this m plus 1 here. So similarly here we have added this formula we know, since this, let me write here, since n.C.r plus n.C.r plus 1 equal to m plus 1 C.r plus 1. Okay, therefore first term, this one as it is, this is equal to um plus 1 v. Now plus this is, if I take um v1 common, this is um v1 common, so it will be 1 plus nc1. This is nc0. 1 means here it is nc0, because this 1 is nc0. This is nc1, right? Into um v1 plus now this one nc1 plus nc2 within bracket into this one mc1 plus mc2. This will be um minus 1 into v2. Okay, let me write it here. Multiplication is within bracket, sorry, let me write it as that bracket is here. So it will be um minus 1 into v2 plus mc2 plus mc3. Okay, this is um minus 2 v3 plus and so on. And finally this value n.C.r plus n.C.r plus 1 in bracket n.C.r plus 1. This is um minus r. This is um minus r vr plus 1. Okay, plus, and final term, let me write here. This is u into vm plus 1. This is the last term. What we get here, so it is the similar type of formula we obtain. What is that? Here it is. First term is um plus 1. This is m plus 1 plus m plus 1 c 1, because 0 plus 1, this is 1 only. Okay, so m plus 1 c1, this is this is um into v, and this is v1, plus this is m plus 1 c2, okay, into minus 1 v2, plus m plus 1 c3, this is minus 2, this one, into v3. Okay, so in this way we obtain the similar formula, and last step is, and let me write here, m plus 1 cr, into minus r plus 1, this one m minus r, into vr plus 1. Okay, m minus r, vr plus 1. Okay, this is n.C.r plus 1. MC here r plus 1, sorry. This is MC m plus 1 cr plus 1. This, for this formula we have taken. If we take n.C.r, then this will be there, then vr is here. This is r plus 1, m minus r 1 less, and vr plus 1. Okay, so this is, and the last term is u into v m plus 1. Similar formula is obtained. I mean, this is the theorem. Means this theorem is true for next number. This is n plus 1. So hence it is true for all the integral values of. Okay, hence the theorem is true. The theorem is true for all types of functions. Is true for all the integral values. All the integral values of n. That means n equal to 1, 2, 3, 4, 5, etc. and so on. All the integral values of n. Okay, so the theorem is proved. Hence the theorem is proved. So this theorem, manual theorem, is very important in case we have to discuss about. Now we have to utilize this theorem to find out these questions. Now let me take these questions one by one. Very important questions. If minor mistake is there, then the question will not be solved. Okay, so let me take them very patiently. Very important questions there. Now first question is, it says y equal to x cube. First question. If y equal to, say, x cube e raised to power ax. Now it says that find out the nth derivative, find the nth differential coefficient of the following functions. Now they are in product form, so we can find out nth derivative of these functions with the help of Leibniz theorem only. Okay, so let me first find out what is y1, first derivative. Now in this case, let me take what is u and v. Let me take here u and v. Here u we have to take e raised to power ax, and v the second derivative which is differentiated. Okay, which is differentiated from initial. Okay, so this can be taken as the x cube. Any polynomial function like this, algebraic function which has the indexes, is taken as the second function v. Okay, because it is going to be differentiated, and when it lasts, the differentiation of this whole, I mean the formula for Leibniz theorem will last only for 2 or 3 terms. Okay, we have to assume whatever polynomial function is given as second function v. Here v is x cube, u is this. What is un then? Because for finding out nth derivative, we have to find out this. First let me find out 1, 2, 3 and so on. Okay, what is u1 then? First derivative, it will be a into e raised to power ax. Why? Because e raised to power ax is e raised to power ax, but ax is not x, so we have to differentiate ax again. It will be a only, multiplied by constant. This is a into e raised to power 1. Then what is u2? u2 will be a square e raised to power ax. Similar value. Therefore, what is un here? Un will be e raised to power n e raised to power ax. The same value. This is y. A n into y was e raised to power, sorry, not y, but this is u only. Okay, so u we have assumed as e raised power ax. Alright, this is what. So un is this, and what is the v1? Here v1 will be 3x square, v2 will be 6x only, 6x, and what is v3? Only 6, and v4 equal to v5 and so on 0. All terms, further terms will be 0. Okay, so the question will last only up to this. So what is what is the Leibniz theorem? Therefore, nth derivative of this function will be what? Therefore, nth derivative, we write here yn. Using, let me write here, using Leibniz theorem. Leibniz theorem. Using Leibniz theorem, is the nth derivative, of the given function, of the given product, will be, here yn is equal to, first let me write un, etc. This will be un into v. First write the formula. This is nc1, this is un minus 1 into v1 plus nc2, right, this is un minus 2 into v2 plus nc3, this is un minus 3 into v3. We have to reach up to v3 only, okay, because after that terms will be 0. Only these terms will come up here. So now let me write the nth derivative. This, what is the un here? This is a raised power n into into e raised power ax. Write the values. E raised power ax as it is. Okay, so un is this an e raised power ax into v means x cube as it is, plus sign. Now nc1 is n only, okay, this is n only. Now nc1 is n only, un minus 1, that means a raised power n minus 1 into e raised power ax into 3x, because v1 is 3x square. Alright, plus n into n minus 1, because nc2 divided by factorial 2. This is a raised power n minus 2 into e raised power ax into 6x plus n minus 1, n minus 2 upon factorial 3 into e raised power n minus 3, e raised power ax into 6 only, plus other terms will be 0. Okay, so this is nth derivative of this. Yn is this. Let me further summarize this. Here it is x cube. Let me write here a raised power n x cube into e raised, if I take e raised power x common, ax common, so let me write here ax is common, e raised power ax is common because every term will contain this. So it is an x cube first term plus n into a raised power n minus 1 into 3x square. Let me write here 3 into x square, 3 and a raised power n minus 1. Okay, then plus this is 2 3 is 6. Okay, so 3 into 3x into n minus 1, okay, into a raised power n minus 2 only. Okay. Alright, then the next term from this term I have written here 3x, and the last term is 3 2 is 6. For factorial 3 is 3 into 2 into 1, that means 6. This 6 is cancelled out. So only n into n minus 1 into n minus 2 into a raised power n minus 3. So this is addition. If I take a raised power n as well common, so what will be there then? Or a raised power n minus 3 common, that can also be taken common. So if I take a raised power n common, divide by n, it will be 1 upon a only. Or a raised power n minus 3 can be taken common. If I divide this by a, this 1 minus a cube will come here. Okay, a square here and a here. So okay, this is also the answer. The same answer is obtained. So can we further summarize? So this is the answer. Okay. Nth term of this function. This is the first question we have done. Now let me take the second question, which is given as a proof. We have to prove it. We have to prove first differential. Okay, differentiate n times the following. Okay, we find out nth derivative of this function. The second function is, it says that 1 minus x square into d square by dx square, second derivative, minus x dy dx, where this is plus a square into y equal to 0. It says that differentiate n times the following. So we have to differentiate this n times. These are the three terms here. First term, second term, third term. So three term polynomial this is. Okay, so first let me differentiate this n times. Differentiating n times this function. Now let me take here differentiating each term n times using Leibniz's theorem. Using Leibniz's theorem, we get, so differentiation of, let me write here dn of 1 minus x square into, let me write here, it is y2. Instead of d square by, let me write it as y2. So what it will be? It will be, here the differentiation of this will be, let me take this 1 minus x square as v and this y2 as u. It will be yn plus 2. Differentiation of u n times, and 1 minus x square, the v as it is, then n by nc1, that means n into yn plus 1 less. Okay, and this is differentiation of this will be now